All right, Chapter 1, Section 1, Master Level. This is SI measurement. So we're going to continue on with unit analysis, but here it says two-step. So you're going to see that when you're using unit analysis, you don't have to multiply necessarily by only one conversion factor. You can multiply by two. In fact, you can multiply by as many as you need. So when applying unit analysis, you can multiply by many conversion factors, which is what I just said. Just be sure the units cancel from top to bottom. So this is really why unit analysis is so powerful, because it's almost a foolproof way to prevent you from making a mistake. Okay? Because if you can't cancel your units properly, you know automatically you must have made an error somewhere. So if I want to convert 1.62 meters to millimeters, okay, again, this doesn't require unit analysis, but I'm just going to demo the process anyway. You could actually do this in one step if you know the conversion factor between meters and millimeters, which you should. There are 1,000 of these in a meter. But you could also go from meters to centimeters, and then from centimeters to millimeters. That creates a two-step problem. So I write 1.62 meters. So that's my initial measurement. And let's suppose I want to convert to centimeters first. Maybe you forgot you couldn't go from meters to millimeters directly. I don't know. So let's say I want to go to centimeters. Well, I want these meters to cancel, which forces me to put the meters down here. And I know that in 1 meter there are 100 centimeters. Okay? So already my meters cancel out. Okay? So the units now are in centimeters. But I want to finish off with millimeters. So I'm just going to multiply again. Okay, so if these centimeters are to cancel, that means here in the denominator I have to have centimeters. And I know that 1 centimeter is equivalent to 10 millimeters. So the centimeters cancel, and lo and behold, the units that I wind up with are millimeters. So to work this out, this is 1.62 times 100 times 10, which is the same thing as multiplying by 1,000. So that gives me 1,620 millimeters. There we go. The next example wants to go from centimeters to kilometers. All right. So you could do this in one step if you know how many centimeters are in a kilometer, or you can do it in a few more steps. So you might want to go from centimeters to meters, and then you want to go from meters to kilometers. You could do that as well. So we begin with the given measurement, so 73.6 centimeters. And let's go to meters first. Okay. So I want these centimeters to cancel, so that means the centimeters has to go in the denominator. So there are 100 centimeters in a meter. So now my centimeters are gone. But I now want to convert from meters to kilometers. Okay. So if that meter is to cancel out, that means the 1,000 meters has to go here. And therefore the 1 kilometer goes up here. So these cancel. And the units I'm left with are kilometers, which is what I want. Okay. So to work this out, this says 73.6 times 1 over 100. And remember, that's exactly the same as just dividing by 100. And same thing here. If you're multiplying by 1 over 1,000, that's just the same thing as dividing by 1,000. So really, I'm taking 73.6, and I'm dividing it by 100, and then dividing it by 1,000, which gives me, let's work this out, just got to count the right number of zeros. That would give me 0.000736, and this is kilometers. Okay. Later on, you're actually going to learn how to take numbers like this, that have lots of zeros here, and express them in something called scientific notation. We'll get to that. But for now, there we are. All right, unit analysis, mass and volume. Yes, unit analysis can be applied to, well, any type of unit you want, not just measurements involving length. So 1 kilogram, how many grams? You should know that as 1,000. For every kilogram, there are 1,000 grams. For every gram, that is 1,000 milligrams. Okay. If I'm talking about volume, 1 liter, okay, you should know that that is 1,000 milliliters. Okay. And if you have 1 milliliter versus cubic centimeters, well, they're actually the same thing. Okay. So if you see 1 milliliter or 1 cubic centimeter, well, they mean the same thing. All right, so we're going to use unit analysis to do some more converting. So we have 5.2 kilograms, and we want to express that in milligrams. Okay. Now, of course, it is possible to convert it in one step if you happen to know that there are 1 million milligrams in a kilogram, but perhaps you'd want to break it up into a couple of conversions using smaller numbers. So we begin with 5.2 kilograms, and let's convert that to grams first. Okay, so we want these kilograms to cancel, so I have to write 1 kilogram here, and you should know that there are 1,000 grams. Okay, so these kilograms are gone, but now I want to go to milligrams, so I got to multiply by, let's see, grams have to cancel, so that means 1 gram goes here, therefore the 1,000 milligrams goes up there, and the G's cancel. This is my final unit. Right. So to complete this calculation, all I have to do is take the number 5.2 and multiply it by 1,000 over 1, or 1,000, twice, which is the equivalent of sliding the decimal to the right 6 places. So that's going to give me 5,200,000 milligrams. There we go. That'd be a nice number to write in scientific notation, but as I said, we'll get to that. Next, convert 3.2 liters to milliliters. Well, that's a one-step problem. So 3.2 liters, okay, and we want to go to milliliters. So I want this L to cancel down here, so I say 1 liter on the bottom, and of course that is 1,000 milliliters up top. So these L's cancel. That was easy, because that's the unit I want. So I just multiply it by 1,000. So I get 3,200 milliliters. That was easy. Convert 13.8 milligrams to grams. That's a one-step problem. So I write 13.8 milligrams, and I want to go to grams. Okay. Well, you should know that there are 1,000 milligrams in a gram. So in order for the mg's to cancel, the 1,000 has to go down here. So the 1 gram goes here. And I'm done, because that's the unit I want. The mg's cancel. So to work out this calculation, times 1 over 1,000. Well, that's just the same as dividing by 1,000. So in other words, the decimal is going to get shifted 3 spots to the left. So that's going to give me 0.0138, and I am now in grams. And there we are. Finally, convert 353.1 cubic centimeters to liters. Okay. Well, don't be fooled, because remember, a cubic centimeter is exactly the same thing as a milliliter. Okay. So I'm actually going to work with this number in milliliters right off the bat. A little long there. There we go. So 353.1 milliliters, same thing, times, and I want to go to liters. Well, I can do that in one step. I know there are 1,000 milliliters in a liter, so the 1,000 goes down here. Otherwise, the units don't cancel. So the mLs are gone. I'm left with liters. So to work this out, times 1 over 1,000, or just divide by 1,000, same thing, and you get 0.3531, and this is now liters. Okay, moving on to scale factors. What is a scale factor? Well, specifically what it is, it's a ratio. A ratio of what, though? Well, if you've ever looked at a picture, or a photograph of a person, an animal, a building, or something like that, of course you know that the size of the image in the photograph is not its actual size. And, well, typically that's a good thing. So a scale factor is actually a ratio of whatever it is we're looking at. It's the apparent size, so it's what it appears to be, divided by the actual size. So it's like what fraction of the actual size is the apparent size? Okay. So this, of course, is a ratio. Let's do an example. Number 1, an object 6 meters in length appears in a photo as being 3 centimeters in length. What is the scale factor? So if the object in real life is much smaller in the picture, this is called a reduction. Just a note. All right. So the scale factor is just a ratio of how big the object appears to be divided by how big, or how long in this case, it actually is. So the apparent size is 3 centimeters. You have to be careful though, because you want your units to be consistent. Notice how the initial measurement is given in meters. So you have to express them both in the same unit. It doesn't matter which unit you choose as long as you're consistent. So I'll stay in centimeters, why not? So scale factor. Okay. This would be 3.0 centimeters divided by the actual size, 6 meters, but I want that in centimeters. So that is 600 centimeters. Okay. And just like in unit analysis, these units cancel out. So a scale factor is in fact unitless. Doesn't have any units. Okay. So we can work this out. So what is 3 divided by 600? Well, that is 0.005. Now, though this number is correct, typically when you talk about a scale factor, usually the result is given as a fraction, or it's actually written in ratio form. So 3 over 600, that's already a fraction. So if you reduce this as much as possible, you actually get 1 over 200. Okay. These are the same thing. In ratio form, okay, I'll just squeeze it in here, I'm running out of room. This would be 1 with the colon to 200. What this tells us is that the photograph is 200 times smaller than the size in real life. So if you're wondering how should you express your answer for the scale factor, well, if the question doesn't say specifically what form to use, you can either leave it as a decimal or write it as a reduced fraction. Of course, if the question is clear as to how it wants you to express your scale factor, then of course, follow the instructions. A tree stands 2.1 centimeters high in a photo. If the scale factor is 1 to 240, what is the actual height of the tree? All right. Well, we know that the scale factor is just a fraction. It's a ratio of the tree's apparent height to its real height. And we are given one of those measurements. Okay? We know the apparent height is 2.1 centimeters. So we're actually going to set up two fractions and set them equal to each other. This is called a proportion. All right, so we know that the scale factor is 1 over 240. That's the ratio. Okay? And that has to be equal to the tree's apparent height, which is given as 2.1 centimeters, divided by its actual height. And we don't know the actual height, so until we do, let's just call it x. Okay, so we've actually set up an equation, specifically a proportion, that will allow us to solve for x. Well, how do we do that? We're going to use a trick. It's a trick that I'm sure you've all heard of before. It is called cross multiplication. Now, this is very, very important. It is extremely critical to understand when you can and when you absolutely cannot use cross multiplication. Okay? If you don't know when to use it, chances are you shouldn't be using it. You can only use cross multiplication if you have a fraction equal to another fraction. Okay? If I had a number over here, let's say plus 2 or whatever, forget about cross multiplication. It doesn't work. Okay? It's just a trick that allows you to solve these problems faster. Okay? But you have to know when you can and can't use it. So sometimes when people do it, they write these little arrows here, hence the cross part of it. And we just do the multiplication. So we start here, this is 1, and we multiply that by the x in the denominator. Well, 1 times x, of course, is just x equals. And then we begin here at the bottom, 240, and we multiply that by 2.1. And this would be 500. Actually, before I even write that down, I'll actually write out what I was multiplying. So this was 240 times 2.1 centimeters. Okay. Now that I will work out below here. Just squeeze it in. Which gives 504, and we are in centimeters. Because remember, this 240 over here, well, that ratio anyway is unitless. Okay, so that is actually the actual height of the tree. Okay, now the question didn't specify what units, so we could actually finish right here, but you could also convert it to meters if you like. So that would be 5.04 meters. Chances are the height of a tree would be given in meters. But there you go. Either answer is okay if the question doesn't say.